Alright, AP Chemistry students, we're going to try this on predicting products. Now let's see if I can get back to the original introduction here, which is on chapter 4. And we're going to be predicting products here. So we have two different parts of learning objective 1. The first is going to be predicting the products, right there. And then the next one's going to be on net ionic reactions here, and those two things go together, but for this I'm just going to show you how to predict products of the different kinds of chemical reactions, so this will go pretty quickly, I think. Alright, so the first kind of reaction that we're going to look at is called the precipitation reaction, and precipitation reactions are a kind of double replacement reaction, and so we can work on double replacement reactions here by showing that the cation always gets swapped. And so we start looking at the two different parts here. I have lead here, I have potassium there, and on the other side I have my nitrate and I have my iodine. And so those are the two parts, the cation and the anion, and so the cation is what gets swapped, so we end up over here with KNO3 and PBI. Now I'm going to show you how to go through and predict these products kind of step by step, because we want to make sure we have the correct chemical formula on the product side. You'll notice that the subscript carried for the nitrate, that's because that's a polyatomic ion, so that stays bonded together. But the 2 over here did not carry, because that's telling us how many of those nitrates we have, so how many of those packages that we have to start with. So we want to use the charges to identify the correct chemical formula and not the subscripts that we started with. So since potassium is a positive 1 charge, nitrate is a negative 1 charge, and the overall charge has to be 0, we end up with potassium nitrate here, so the correct chemical formula. Where lead over here is positive 2. Now, I know this because of lead's charge on the reactant side. It stays the same. So lead here starts out as a positive 2. I have 2 nitrates, each one's negative 1, so that's how I know it's positive 2. So it goes to positive 2 on this side. The iodine is negative 1, that does not equal 2, or excuse me, does not equal 0, so we have to have 2 iodines on this side. One of the things that we want to start doing though is identifying the precipitates, because that will be important for our next step of predicting or writing net ionic reactions. So if we go here, potassium is an alkali metal, and so that's going to be soluble. Nitrates are always soluble, so this is for sure soluble. Halides, like iodine, are usually soluble unless they're with lead, mercury, or silver, so this is not going to be soluble. This is going to be a solid. Alright. Let's try just one more. We have our silver switching places with our barium, so we end up with silver hydroxide and barium nitrate. Same thing, that's the skeleton. I'm going to check chemical formulas. This is +1. We know that silver is always +1. Hydroxide is -1, so we're good there. Barium is +2. Nitrate is -1. So we have to go through and show the 2. Now when you're done here, guys, you want to make sure that you don't have those charges listed in your final answer. That's not appropriate. So there you go there. Identify the precipitate. It's the silver hydroxide. Alright. Acid-base neutralization reactions. There are two different kinds of neutralization reactions. The first one's acid-base, and we'll go through here. In an acid-base reaction, we always produce water, and then whatever is left. We used hydrogen and hydroxide to make water, so we're left with sodium and chlorine. The cation always gets listed first, the metal, and then we can identify charges to make sure we have the correct chemical formula. Sodium is +1, chlorine is -1, so we're fine there. Oh, one thing, ladies and gentlemen, I'm not doing here is balancing. Maybe I should, but that's just the next step that I'm expecting you to be able to know how to do. Alright. Let's try one more. Yeah, this will be okay. We have, again, oops, don't know why I just did that. Going back to precipitation reactions, we have our hydroxide and a hydrogen that makes water, and we're left with barium nitrate. Again, similar to one that we saw before. Water is a liquid. We should show that. Barium nitrate is going to be like this, and then we balance, so we can show that real quick. We would have a 2 here and a 2 there. So always produces water from the hydroxides and the hydrogens and whatever is left. Acid carbonate reactions is the next kind. And this is a little bit different because it produces that water and carbon dioxide and then whatever's left. In order to make those two products, we use everything from the acid that makes the acid, and everything from the carbonate that makes the carbonate. Now, the carbonate is a polyatomic ion. However, in an acid-carbonate neutralization reaction, it does get broken up into its pieces. So we're left with water, carbon dioxide, and that takes care of this, and we're left with sodium acetate. Now, in class we talked quite a bit about this acetic acid here and how it is an organic acid, specifically a carboxylic acid, and carboxylic acids always end in COOH. And that hydrogen right there is going to be the one hydrogen that is ionizable. This is what makes this thing an acid. So that's the acid portion of a carboxylic acid. It mixes with the carbonate to get water, carbon dioxide. That's going to be liquid. That's going to be a gas. And then we're left with our sodium acetate, which is still aqueous. Let's try one more. We'll try this bottom one because this one's pretty similar to what we just did. We use the carbonate here, we use the acid here, we get our water, and we get our carbon dioxide, and we get whatever's left. It's going to be NH4SO3. Liquid here, gas here, that uses up the carbonate, that uses up the hydrogens. We're left with that guy there. And charges to identify the correct chemical formula. Ammonium is +1, sulfite is -2. So we have to do that. Make sure those charges don't stay. Alright, and then we can balance. Looks like 1, 2, looks like it might be balanced the way it is. So we're good. Alright. Single replacement reactions. There are 3 different kinds of single replacement reactions that we're going to go over. We have the acid plus the metal. We have a metal replacement that's dependent on an activity series. We have the halogen replacement, which is dependent on an activity series of the halogens. Acid metal first. These are pretty straightforward. Anytime we have an acid metal replacement, we get hydrogen gas as one of the products, and then we get the other part, MgCl. Come up with the correct chemical formula. Magnesium's +2, chlorine's -1. There it is. So there's the acid metal replacement right there. The magnesium is replacing the hydrogen. So we get the hydrogen by itself. Since hydrogen is a diatomic, it's H2. Same thing here. The hydrogen and the copper are going to switch places, so we end up with CuNO3 plus H2. Now this one is kind of a weird one because we don't know what the charge is on the copper. It starts out as a 0. Any element by itself without being bonded ionically is going to have a charge of 0. So now it's CuNO3. And since we don't know the charge, we're just going to leave it as is because one of cosset copper's possible charges is +1, so we could do that. The other one would be +2, and we could do that. But since we don't know, we're just going to leave it there. Metal replacement. Now, this is based on what's called the activity series of metals. And I don't have one on the screen to look at, but I will tell you that aluminum is more active than copper. So in order to determine if a chemical reaction occurs, we look at an activity series to see which one is going to be more reactive. If the one by itself is more reactive, it'll swap places with the one that's in a chemical compound. This is right here. This is the chemical reaction we did in that first lab, the empirical formula of the copper chloride hydrate. The aluminum was switching places with the copper. The copper turned out in solution, and we were able to measure that. And then the aluminum chloride was left to dissolve. So this is going to be aqueous here. This is going to be our solid. And we can come up with the correct chemical formula. Aluminum is +3, chlorine is -1, so there it is. Try one more here. We have the sodium replacing the copper. So we end up with, again, copper all by itself. Sodium is more active than copper. Again, there's a table to look up. I don't have one over here like I should. I do have one in front of me, but I can. We'll look at this more closely in class. So we have Na2CO4. Sodium is +1, sulfate's -2. Okay. Let's try the very last one called halogen replacement reaction. Now this one has an activity series as well. But it is really easy. Those are the different halogens that we have available, and the activity series reacts just in the order of their appearance on the periodic table. So fluorine is the most reactive, iodine is the least reactive. So fluorine, since it's more reactive than chlorine, is going to switch places here. So we're left with sodium fluoride, and we can have chlorine gas all by itself. Now, that chlorine gas is a diatomic, so Cl2. NaF is the correct chemical formula for that guy, and then we can balance. I haven't been doing that, but there it is. Try one more, calcium bromide and chlorine. So we'll switch those two. Chlorine is more reactive than bromine, so it will switch places. We have CaCl plus bromine by itself. Calcium is +2, chlorine is -1, so there's our CaCl2. Bromine is a liquid, and we can balance it. It is. Alright guys, that was the work on the different kinds of reactions and how to predict products. We'll go over a little bit more closely and carefully how to do net ionics, and also review predicting products when I do that. So